Right, hi Year 10. This is us carrying on with the crude oil topic that we just started. Okay, so you've got a couple of little things to think about before we move on to the next idea. So think about ways that oil is useful to us. So in the video on Monday I talked through some ideas. You've got some pictures to help you. Okay, so this one is a really big clue. Okay, one way that we use it. And then I talked about the petrochemical industry. Okay, so what else can we use crude oil for? And then we need to think, where does it come from? Okay, so how is it that we use these two pictures, okay, to actually drill oil and extract it from the ground, and why is it there in the first place? How is it actually formed that it's under the ground that we are going to extract it and use it for all these different functions? Okay, so pause the video and write some notes about those answers. Right, so when it comes out of the ground, crude oil is this really thick, black, sticky, gloopy liquid, okay? It isn't heavy in terms of it will float on top of water. So if there is an oil spill, okay, from an oil rig or an oil tanker, it will float on the surface of the sea, okay? But it's very, very sticky and it's very, very thick. Sometimes it's that very, very black, but it's quite often sort of a dark brown. It's really sticky and gloopy and not very nice, okay? But it depends on which mixture of hydrocarbons there are in it. And remember, we said a hydrocarbon is a compound that only contains hydrogen and carbon. Okay, so crude oil, if we thought about it in terms of the work that you did on Monday, it would look like this tangle of spaghetti chains. Okay, so the black dots in this are representing carbon atoms, the white dots are representing hydrogen atoms, and each one of these is a chain, but remember we said that the chains can be of different lengths. So in this corner here you've got quite a short one, and then running across the middle you've got a very long one, and they're all tangled together. Okay, so it's a mixture. They're not joined together, they're not chemically joined together, but they are mixed together and they're all in a tangle. Okay, but in order for them to be useful to us, we have to be able to separate them. Okay, so we've got some with long chains, some with short chains, and then everything in between. But we need to be able to separate them. So we've got lots of uses of these different types of hydrocarbons, okay, but we need to separate them for them to be useful. So we've got things like petrol and diesel and kerosene, which is used for aeroplanes, like I said the other day, bitumen, which is that really thick tar that they put on the roads. So all of those chemicals are in there, but we can't use them until we separate them into the different bits, okay? And we do that by using fractional distillation, and we call each of these different compounds a fraction. Okay, I'm going to talk through how fractional distillation works. So we have to separate it. Now in reality, the oil refineries where this is done are huge. They're almost like small towns themselves, and it's done, the separating is done within these columns called fractionating columns. Okay, and this is what they would look like in real life. Obviously we're going to look at it on the inside in terms of a diagram. Okay, so what you have at the bottom is a very, very large furnace. So this part here is the furnace. Now the oil gets piped through the furnace, okay? It doesn't burn it, but it will heat it up. So as the oil flows, it's heated to 370 degrees, okay? Now some of those chemicals, some of those hydrocarbons, at 370 degrees, it will cause them to evaporate. Okay, so they'll boil up and they'll turn into a vapour, into a gas. Now, if you have bubbles of gas inside a liquid, then those bubbles are going to rise. So if you pour yourself a glass of fizzy pop, the bubbles are going to rise to the surface because the gases are lighter than the liquid, and that's exactly what happens in the fractionating column. Okay, so some of the chemicals, some of the compounds will turn into gases, and they will rise up through this big column. Okay, and that's what separates the different fractions. So all of the oil, it's not being burned there, it's being heated up. Okay, so the oil's inside, and then it will enter the fractionating column. Okay, so the ones that have turned into a gas will rise up through the column. Okay, now this is the black ones at the bottom are the very, very thick ones that have a very high boiling point. So they will stay as a liquid even at 370 degrees. the chains are too long, they're too thick and too gloopy and too sticky, and they will stay as a liquid even at 370 degrees. Okay, these other ones that have evaporated and turned into a gas will start to rise up. Okay, so I'll just show you the first little part. This is called a bubble cap. Okay, so what happens is that the gases rise up. As they hit the top of this, some of them will start to cool down again, and some of them will start to turn back into a liquid, just like you get steam on the window that it was hot from the shower or from the kettle, and when it hits the cold surface of your window it turns back into condensation. Okay, so that's what's happening in this first tray. So one of the fractions, it's risen up, but then it's hit this surface, it's cooled down, it's turned back into a liquid. Now if I didn't have that cap on there, it would just drip straight back down again. Okay, so because it's in this part, it collects in that tray. Okay, and then each fraction does exactly the same thing. So the next one goes up. So each of these layers, okay, is as you go up the fractionating column, because you're moving away from the furnace, they're starting to cool down. Okay, so down here it's still very, very hot. That stayed as a liquid. But as the gases travel up, they start to cool down because they're moving away from the heat. Okay, so it might be that up here the temperature's only at 50 degrees. Okay, so some of them have risen up, they can stay as a gas up to here, but then they also condense and form this liquid in the trays. So each of these trays will contain a different type of hydrocarbon. Okay, now you can already see there's a pattern. We'll talk about patterns a bit more later in the week, but you can already see that the ones with the long chains, the very ones with a high boiling point, are very, very dark. And as you go up through the column, the fractions, the hydrocarbons, actually get paler, so the colour gets lighter. Okay, so in terms of the very top ones, some of them actually don't even condense, they will stay as a gas. Okay, so some of these hydrocarbons have got such a low boiling point that they won't condense, they actually stay as a gas. Okay, so let's think about what each one of these fractions are called. Okay, so at the very, very top you have liquid petroleum gas, or LPG. Okay, that's often put into gas bottles and it's used as a gas. Okay, so it's compressed into the bottle, so it'll sound like it's a liquid, but when it comes out, it's a gas. Okay, it boils at less than 0 degrees. Okay, so at room temperature, if it came out of the gas bottle, it would be as a gas rather than a liquid. So LPG that's what it's called. Now, it's important that you relate the properties to the length of the carbon chain, and you'll notice a pattern in a second. So the LPG has got a carbon chain of only 1 to 4 carbon atoms. Now, remember our naming system, monkeys eat purple bananas, so it would be methane, ethane, propane and butane, okay, with those 1 to 4 chains. Now, as you move further down, you'll notice that the carbon chain gets longer. Okay, so this is petrol. I know they've called it gasoline, but we're talking about petrol. That's got a chain of 5 to 10 carbons, and it boils at a higher temperature. Okay, so already we're starting to see a pattern. Naphtha is another one that's got a slightly higher, longer chain, and it boils again at 22. So these two, gasoline and naphtha, are quite tricky to separate because they're quite similar. Okay, and it will boil between 20 and 180 degrees. Okay, so those two are quite similar. Now kerosene, this is airplane fuel, or like it says there, it's also known as paraffin oil. This time it's got from 10 to 16. So again, the chain is getting longer and it boils at a higher temperature. So it has to be closer to the bottom. Okay, diesel oil, right, 14 to 20 carbons. My carbon chain has got longer. It boils at an even higher temperature. Okay, so you should be noticing that the patterns, right? So lubricating oil, 20 to 50 carbon atoms, boils at 370 to 600 degrees. It's not got a specific boiling point because it's still a mixture. Okay, so it doesn't have, like water boils at exactly 100. It has a range of boiling points because it's still a mixture of carbon chains. But they're getting longer as you go down the fractionating column. So this one is 20 to 70, it boils at more than 300, and then the residue is the really, really long chains, and it doesn't boil. Okay, so it stays as a liquid, and that's also called bitumen, which is the stuff that they put on the road. So like tarmac, if you've ever on, like sometimes in the summer and it starts to melt a little bit and you stand on it, it's really, really thick and sticky. Okay, so as you come down the fractionating column, the carbon chains have got longer, okay, the colour has got darker, and the boiling point has increased. Okay, so this is really, really important in terms of thinking about our patterns. Now, I've got another little summary diagram which you'll need for the work you're going to do. Okay, I'm just going to flick through it so you've got all the information. Okay, so you've got your ideas here in terms of the temperature decreases. So as you move away from the furnace, it starts to cool down. Okay, so you've got your gases at the top, which has got the lowest boiling point. The boiling point increases as you go down the fractionating column. They get darker as you go down the fractionating column, and their carbon chains get longer as you go down the fractionating column. Okay, now you might have to pause the video and go backwards and forwards and check what I've said and look at the jobs, or what we use is the uses of the fractions from this slide. Okay, so you might have to go backwards and forwards and keep pausing it to write the notes, but there is a sheet on class charts for you to complete about fractional distillation and these different hydrocarbons.